Hi, welcome back. This is Math 1620, and I'm going to do the pre-test, so basically the test 3 review today. And right, so let's dive right in. So you want to do, again, as usual, you want to do the test before you watch this video, and then watch the video, and hopefully your answers are similar to mine. So, I expect you to use the techniques that I show in the video, or you've contacted me prior to the test and said, hey, I have this technique maybe you learned previously, and then you bring that to my attention. Otherwise, I'll expect to see my methods. Please read the directions, so show all work, and I even say at the top of my test, you should have methods consistent with my techniques discussed in my videos. Okay. The first couple problems are just limit problems. So these problems came up prior to actually studying the type of sequences that we are interested in particular the sequence of partial sums, which we applied to these infinite series, right? So in this case, all you got to do is basically take the limit. If the limit equals something, then it's convergent. The sequence is convergent. If the limit does not equal something, if it's does not exist, then it's divergent. Or if it goes to infinity or negative infinity, it's also divergent. Okay, so problem 1, I added in some factorial notation. We should all be kind of able to reduce this notation. We could reduce the expression right here, and I would probably just do a brute force and start subtracting, one at a time. N plus 2 times n plus 2 minus 1 is n plus 1 times n plus 2 minus 2 is just n, and always goes to 3 times 2 times 1. In the denominator, you have n plus 1 times n plus 1 minus 1 is just n times n plus 1 minus 2 is n minus 1, all the way to 3 times 2 times 1. Look for a common cancellation, so it looks like this. Everything below the n plus 1 will cancel, and you're just left with n plus 2. Okay, so that's the nth term formula for the terms of the sequence. So if you wanted to list the terms, which I wouldn't do, a sub 1 would be 3, a sub 2 would be 4, etc. So we are interested in long-term behavior of sequences for our work. So we would want to take the limit as n goes to infinity of the a sub n formula. And in this case, it's going to shoot off to infinity, and therefore the sequence is divergent. Sequence diverges. Okay. Okay, good. Number 2, same kind of problem. And I talked about number 2. They don't do a good job of explaining why or how to show that this thing is divergent in any books that I've really seen from calculus. The way you approach it, maybe you learn more in advanced calculus where you start looking at subsequences. Okay, so if you can find any subsequence which does not, or rather if you can find 2 subsequences which go to 2 different places, then overall the sequence will diverge. The way I approached these problems was to say, look at the even terms, look at the odd terms, and if they're not the same, then the sequence will diverge. This is one of those rare instances where you can kind of do the logical, is it converse or inverse error, and it still pans out. If the even terms and the odd terms have the same limit, then it is convergent. Okay, so is that the contrapositive? Well, anyways. The way you'll approach this is to look at the even terms. So the formula for the a sub n formula would be negative 1 to some even power. So usually we say 2n, right? We want to look at a sub 2n basically. So wherever you see an n, you're going to replace it with 2n. And then in here we have 2 times 2n all over 2n plus 1. And so negative 1 to the 2n, we kind of got some experience dealing with that stuff from our work with the convergence of at endpoints when we're doing intervals of convergence, right? So this would be -1 squared to the n, which is 1 to the n, which is just 1. So the even terms are all positive, and then the expression for the even terms would be 4n all over 2n plus 1. And then we could take the limit of these terms, this expression for the terms of the even terms of the sequence. And of course, you could do the circling trick, and you get the limit of 2. So the limit of the even terms is just 2. Then we want to do the odd terms. That you can think of those as the 2n plus 1 terms. And in that case, you're going to have -1 to the 2n plus 1. That thing's going to be negative. It'll just be -1, right? And then you have 2 times 2n plus 1 all over 2n plus 1 plus 1. Okay? So that -1 to the 2n plus 1 is equal to -1 to the 2n, which we just kind of did above it, is equal to 1. And then times -1 is just -1. So these terms are all going to be negative, right? So I have negative, and then distributing 4n plus 2 all over 2n plus 2. So taking the limit, in this case, limit as n goes to infinity of this expression, 4n plus 2 all over 2n plus 2, that thing is just, again, you take the ratio of the high degree terms. There's a negative out in front, so you got to be a little careful. -4n over 2n. This would be then the limit of -2, so -2. At the end of the day, the limit of the even terms does not equal the limit of the odd terms, so therefore the limit does not exist. And therefore it's divergent. Okay? So I really want you to do this because it's your first kind of introduction to dealing with subsequences, and it's not shown in the book. The book is kind of just, we're going to have all these in-depth proofs, but for this we're just going to say it's oscillating. It's divergent by oscillation. And no, I don't like that. That's cheap. So anyways, expect to definitely see one of these, and I want to see this type of analysis. And you can kind of get away without having to worry about the 2n or the 2n plus 1 if you just note that the limit of a sub n, when it's odd, you're always going to have a negative. So it'd be basically -2n all over n plus 1, and then the limit of that's -2. When it's even, it's just going to be positive, basically 2n all over n plus 1, and the limit of that is just 2. So you can kind of avoid having to learn something if that's your game. I think it's not always a good game to play because it could come back and bite you, but I need to see some sort of, I want to see some sort of analysis like this. Do not just write oscillation. Do not just write does not exist. If you do that, then, +1 out of 5. Okay? Okay, so anyways, let's look at number 3. So find the sum of the series, and I will tell you throughout the test kind of which test I need you to use. I need you to give me evidence that you learned how to do all of the tests. So number 3 and 4 are basically 9.2 problems. That's where we got our first 2 types of series, the telescoping series and then the geometric series, right? So in these cases, you can actually find the end value of the summation. So we learned that we can analyze infinite sum or a series as a sequence of partial sums, right? So this is the same as, it's the limit of the sum of going from n equals 1 to k as k goes to infinity of a sub n. And basically this object here is like these a sub n formulas above, okay? And we wanted to be able to get our hands on this formula, and we found in general that's not possible. But in these 2 easy examples, it is possible, okay? And this is basically our sequence formula, but the way we approach it is it's a sequence of partial sums, okay? And if that formula, the limit of that formula equals something, then we say that this series sums to whatever it equals. So you could kind of think of it as adding up to something. Okay, so problem 3, we are dealing with somebody is, hold on, the phone keeps ringing, sorry. So I've lost my pen, I don't know what I was doing. Okay, hold on 1 second. Pause the video again, just go and find my pen. All right, anyways, this guy is telescoping. I'll even tell you, on the test you can do partial fractions, or that's the hint. So what do we have? Okay, so we set it up 1 all over n times n plus 2. That'll equal a all over n plus b all over n plus 2. And we want to solve for a and b here. So multiply through by n times n plus 2. You get 1 equals a times n plus 2 plus b times n. Then substitute values of n that eliminate either a or b. So I'll try 0. So I get 1 equals a times 2. In other words, a is 1/2. And then try negative 2. So I get 1 equals negative 2b. So b will be negative 1/2. Okay, great. So I want to rewrite this thing as the limit of a finite sum, and that finite sum is going to be that formula for the terms of the sequence, in this case a sequence of partial sums. Okay, so I'm going to rewrite this as a limit. I've already used the n variable, so I'm going to put a k up here at the top of the summation, and I'm going to drive k to infinity, and on top of everything else I'm going to rewrite now the terms of the sum as they have been established in the decomposition. Okay, so I get 1/2 over n minus 1/2 all over n plus 2. And then I'm going to expand this summation, this finite sum. One other thing, you could factor out constants from the summation. Because now it's finite, you can do that. So there are issues if it's an infinite sum, but if it's finite, you can definitely move the constant out. Okay, so we'll have 1/2 times the sum from n equals 1 to k of 1 all over n minus 1 all over n plus 2. Right? Alrighty then. Okay, so finally I'm going to go ahead and expand that sum. And usually the way I approach it is to do the first couple terms and the last couple terms just so I can see the pattern of cancellation. Okay? So I get 1/2 times, so when n is 1, I'll have 1 over 1 minus 1 over 3. When n is 2, I'll have 1 over 2 minus 1 over 4. When n is 3, I'll have 1 over 3 minus 1 over 5. And, just for good luck, I'll put one more in here. 1 all over 4 minus 1 over 6. And then plus dot, 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 plus. And now I usually just put in the last 3 terms. Okay, so the last term is k, or n equals k. The second to last term, k minus 1, and then the third to last term, k minus 2. Great. Substitute. K minus 1 plus 2 is k plus 1. Okay. And then start looking for the pattern. Right, the pattern of cancellation. So it looks like what's happening is that the second term in each one of these kind of binomial expressions is jumping the term in front of the binomial in front of it and canceling with the first term of the binomial after. So it looks like the 1/4 is going to jump and cancel with this. Then the 1/5 will jump and cancel in the dot, dot, dot baloney. And then, whoops, the 1/5 will cancel. And then the 1/6 will jump and cancel in here. And then you could kind of extrapolate the pattern into the Ethernet here, the the dot, dot, dot. So it's the second term in the binomial will jump one binomial and then cancel the first term like that. Okay, so there's going to be a guy here. It's going to jump this term and then cancel here. The 1 over k, I can see, is going to jump this and cancel with that. And then that's it, right? Because the 1 over k plus 1 can't jump any further because there's not another term after the one it would jump. Okay, patterns can be different for different situations. I've seen some really crazy patterns in the past. And just, you know, I'm not going to put anything crazy on the test, but just be aware if you want to become a teacher or something, you may have to deal with some crazier patterns. Anyways, let's see what's left over, right? So I have limit as k goes to infinity of 1/2 times 1 plus 1/2 minus 1 all over k plus 1 minus 1 all over k plus 2. Okay, so the 1 over k terms are both going to go to 0. Those are L over infinity terms. And then you're just left with all the constant material. So 1/2 times 1 plus 1/2, that's 3/2. And then multiplying that together, you get 3/4. Okay, and that truly is the sum of that series. It's convergent. It's definitely true. And there's your answer. Okay, number 4, we're also finding the sum of the series. Number 4 is kind of a it's geometric, right? So the way these work is that the first term is your a value, and then for the r value, you take the ratio of 2 consecutive terms. So I'll just take the second term, which is -5, all over the first term, which is 25. Simplify, and it looks like our r value is -1/5. Okay, great. So this will be the sum from n equals 0 to infinity of 25 times -1/5 to the n. And you can check, you know, plug in some n values. So this should be n equals 0. If I plug in 0, yeah, I get that. Plug in n equals 1, you get 25 times -1/5, which is -5. So it seems to work, okay? All right. At this point, then, you need to find the sum. Right, it is geometric. The a value is 25. The r value, and we are interested in the absolute value of r for this test, is going to be equal to 1/5, which is definitely less than 1. That tells you it's convergent. Right? So you need to make sure it converges at all before you go and find the sum. Once you determine it's convergent, then it's just a matter of using the a over 1 minus r formula. Be a little careful. The r value is negative, so I have to go 1 minus minus. That'll be 25 all over 6/5, which is 125/6. Okay. Sadly enough, when you're dealing with series in real life, you're typically not going to be able to get the exact sum, right? So what we ended up doing was developing all these convergence tests that tell us whether or not a series is convergent. And then later on, we said, okay, if this thing is convergent, all we have to do is use maybe 20 terms, depending on Taylor's theorem, what it says, in order to get a good approximation. And I think in general, you could probably just use the first couple hundred terms and you'd have a good approximation. It seems like, at least in the examples we see, maybe it's misleading, right? I don't know. I haven't investigated that further. Haven't had the desire to do that. But anyways, convergence versus divergence tests is what we encountered next in the class. And the first test we saw was the integral test. So usually if you see a summation such that you could take the integral of the terms of the series, then you're thinking, okay, integral test. You don't want to do the integral test though, right? Because to do the integral test, you have to go through and check 3 things based off of the function, which kind of mirrors the terms of the series. In our case, it'd be 2 all over 5x plus 5. And we're on the interval from 1 to infinity. Okay. So the 3 things, we have to prove it's continuous on that interval. I'm going to allow you to assume that for the test, so you don't really have to show me a proof. I'm going to let you assume it's positive. again, you don't have to show me a proof of that fact. If you want to get better at proofs, it'd be like a direct proof. You take a proof class. They have those at, Ohio State. You take a math logic class, or you can take at some of our other colleges like a discrete math, and sometimes they'll do proofs in those classes. Okay. So, anyways, what I want you to prove is decreasing, and you definitely have the tools to prove this because it's based off the derivative, right? So, if you could show that the derivative is always less than 0, it's always negative, then that implies that the curve is always decreasing. Okay. So that's what I want you to show. So in order to pull that off, I'm going to rewrite f of x as 2 times 5x plus 5 to the negative 1. And then the derivative f prime of x, power rule. So bring on the negative 1 exponent. Subtract the old exponent by 1, so get negative 2. And then chain rule on the guts. So the times the derivative of the guts, which is 5. So our expression is negative 10 all over 5x plus 5 squared. The numerator is negative, the denominator is positive, so that is definitely less than 0. And that implies the function is decreasing on that interval. Okay, so yes. And again, on the test, that's all I want you to do. It's just the decreasing part. And it should be this type of find the derivative proof. Okay. Okie dokie. So once we've established the criteria are fulfilled, we can apply the integral test. And maybe part of the point is you just can't apply any test you want, right? You need, there are usually some sort of criteria involved before you can apply the test. Maybe that's the point. I don't know. So anyways, let's take a look. I need to investigate this integral, and if this integral converges, then the series will also converge. Okay, it doesn't say what it converges to, but we have this data, and we can say, okay, the series works, and then use it to get an approximation. You use the first 100 terms, and then okay. So anyways, let's rewrite it as a limit. Replace the bad bound or the bad limit with the variable. Got 2 all over 5x plus 5 dx. I need to do a u sub on this character for the denominator. So you should be showing me your u subs on the test. This will be the limit as b goes to infinity. Well, let's drop all the fancy notation, the bells and whistles, while we're in u sub land. So I have 2 all over u times du all over 5. I can factor out the 2/5, and then I get the integral of du over u, which is a natural log. So that will equal the limit of 2/5 ln absolute value. Let's go ahead and it'll be u, but let's go ahead and back sub just for the sake of my own sanity. We can put all the bells and whistles back in. And then we will evaluate the antiderivative and then take the limit. Okay. So we have the ln of the absolute value of 5b plus 5 minus 2/5 times the ln of the absolute value of 10, which is just 10. Okay. Okay, so the limit of this natural log, so you're putting in b values going to infinity, so it's like ln of 55, ln of 505, ln of 5005. So what's happening is that the y values are getting bigger and bigger and bigger, and that first part is going to infinity. Then you have minus some number, which is finite and not even changing. So it's just going to equal infinity when all is said and done. In other words, both diverge. Okay. So don't forget the main point of the problem is determining whether or not the series diverges. So at the end, I should see some sort of conclusion telling me about the subject at hand. Okay, then we have comparison tests. So one thing we also did in the integral test section were the p-series. So we have these, it's mainly 2 series that we can kind of visually identify easily as either being convergent or divergent. And then we sometimes see things that look really, really similar to them, right? So if we could make some sort of comparison between the known series and the unknown series, then we could conclude that it's either divergent or convergent, but we can't kind of just do it half-heartedly. We actually have to go through these tests, okay? And the way I've set it up in the notes and in the videos, I want to see 3 steps. I want to see for the comparison test, so the direct comparison test is what you see in number 6. I want to first see this inequality. Okay, so if you want to prove the thing is divergent, you have to find a series that has terms that are less than the given series such that that series is divergent. If you want to prove convergence, you need to find a series such that the terms of that series are bigger than the terms of the given series. Okay, so anyways, in this case, usually I just start by kind of chopping off the constant parts and then seeing what I have. So in this case, the inequality, what have I done? I've decreased the denominator here, so it's really 7 to the n plus 4 minus 4. You take away 4, you decrease the denominator, therefore you increased this other expression, and we have this inequality. So if those are the terms of a series that's convergent, we're good to go. Okay. So what is that series? Step 2, you have to talk about it, right? So maybe not all that familiar in that form, but if you rewrote it a bit, now we see, okay, it's geometric. The r value, in particular the absolute value of r, is 3/4. That is less than 1, so therefore it's convergent. And yes, you need to say that. You can't just say it's flip a coin. You know, I'm flipping a coin here. No, you have to give me this. And for my problems, it's either going to be geometric or the p-series, right? And you're doing a comparison. So for geometric, it's, you know, r value, and then is it convergent or divergent? For p-series, it's p-value, and then is it convergent or divergent? So, of course, you have to have those criteria memorized as well, right? So r value, absolute value of r has to be less than 1 for convergence. For p-series, the p has to be greater than 1 for convergence, okay? All right, so anyways, what am I doing? Now I make a conclusion, right? So if basically the series where the terms are bigger is convergent, it forces the series where the terms are smaller to be convergent. So here, both series converge. Okay, so I should see this 3-step process on the test. I've kind of made it so it's easy for you to tell me what I need to hear and do your job. Okay. Anyways, let's look at this guy. This is then, you can see in problem 7, use the limit comparison test. So again, make sure you read directions. And again, I want a 3-step. So the first step is to do this comparison, make up this comparison series. So you could circle the high degree portions, and here I'm going to be comparing with 1 all over the square root of n squared. When n values are greater than 1, and of course we have to kind of cheat a little bit and not include 0, so we'd have to go n equals 1 to infinity. But supposing that the n values are positive, we can reduce this to just be 1 over n, and that guy is the divergent harmonic. Right, so you just write divergent harmonic. Then secondly, I need to do this limit of the ratio of the terms of these two series. So I have n squared plus 9 all over 1 all over square root of n squared. That will be the limit of the square root of n squared all over the square root of n squared plus 9. And again, you could circle off the high degree parts. Just get the limit of the square root of n squared all over square root of n squared, which is the limit of 1, which is equal to 1, which is greater than 0 and finite. So therefore, both have the same behavior. Okay, so the kind of pitfall here is people think that, well, if it has a limit, it must be convergent. No, you have to go back and think about the proofs, okay? So you're just kind of existing on the surface level, and that's kind of one of the reasons why I did those proofs, is so you can understand, hey, there's a lot more going on than just what's going on at the surface. So anyways, yeah, it's telling you that both series will have the same behavior. In this case, both diverge. But anyways, let's move on. So the next section in the book, we started working with series that may not necessarily have all positive terms, and in particular, alternating terms. So number 8, I want you to use the alternating series test to prove whether it's convergent or divergent. So there's always 2 steps in this test. First, you're taking the limit of the a sub n portion of the series. So I should not see any negative ones floating about. Okay. At the end of the day, the limit of this has to be 0. If it is not 0, then you can conclude that the series is divergent. Okay. Secondly, you need to show that the terms of the series are decreasing. Okay. And you can't just look at a couple examples. So that always kind of scares me when I see a student just write n equals 2. Like here's what they do. They put like n equals 2, and it's 1 all over 8. And then n equals 3, and that's 1 all over 13. Therefore, it's decreasing. No, that won't work. Okay. And why won't it work? It's because if you drove the work going 100 miles per hour twice in a row and you got away with it, are you always going to get away with it? No. Okay. So you need more proof than that. And I mean, even what we're doing right now isn't all that great of a proof, but it's more than that, you know. So anyways, n plus 1 squared plus 4, that's a sub n plus 1. So in step 2, I'm doing kind of this ratio comparison between the terms of the series and showing that the terms are, that this ratio is less than 1. In other words, a sub n plus 1 is less than or equal to a sub n, and therefore it is non-increasing, which is basically decreasing. Okay, so I have n squared plus 4 after I reciprocate all over n plus 1 squared plus 4. Clearly the denominator is greater than the numerator, so I could say that's less than 1. And then those 2 factoids together add up to convergence. Okay, so I'm not going to put any of the conditional convergence or the absolute convergence stuff on the test. Those are in the homework. I hope that's good enough for you. Let's look at problem 9. So now we're into the ratio and root tests, which are kind of the workhorse of the intervals of convergence. So let's take a look. There are 3 criteria for these tests. The rho, if that's less than 1, it's absolutely convergent. If rho is greater than 1 or equal to infinity, it's divergent. If rho is equal to 1, then, oh, you're out of luck, try something else. Okay, so here we go. It's the rho value is the limit of the absolute value of the ratio of a sub n plus 1, which is 4 to the n plus 1 over n plus 1 to the 7, divided by, in other words, multiplied by the reciprocal of a sub n, which is n to the 7th all over 4 to the n. Okay, so we simplify this guy. The limit of, so I could, 4 to the n plus 1 all over 4 to the n is just 4. And then multiplying straight across, I have n to the 7th. So this, you just subtract the exponents, and that'll equal 4. Okay, 4 to the n plus 1 minus n is 4 to the 1. Then the other stuff left over. So here we can circle off the high degree parts. So the high degree term in the numerator, there's only one term, so it's 4n to the 7th. Then in the denominator, if you were to sit there and multiply that out, the first term, the leading term, would be n to the 7th. Okay, so we can circle those off and then do the limit of that. So it would be 4n to the 7th all over n to the 7th, which is basically just the limit of 4. So that will equal 4. Okay, so what does that say? Well, that's greater than 1, so therefore it is divergent. I got another one for your test here. N equals 0 to infinity. So this time my rho value Again, it's the limit of this ratio. I have 3 to the n plus 1 all over n plus 1 factorial times its reciprocal. So I got to do a little bit of work with factorials. First, I kind of note that this guy is just 3. So I'll have the limit of the absolute value of 3, and then times n factorial, brute forcing that, it's n times n minus 1 times n minus 2, blah, 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 3 times 2 times 1. Smushing that in. And then I get n plus 1 times n plus 1 minus 1 is n times n plus 1 minus 2 is n minus 1. Look for a cancellation if there is one, and yeah, okay, all that junk will go away. So I get the limit of 3 all over n plus 1, which is an L over infinity form, and therefore it's equal to 0. So that thing is going to be convergent, absolutely convergent. You could just write convergent though. Okay, great. So that gives us all the tools that we need in order to work with these, what will become the power series representations for functions, right? And those will be basically the Maclaurin series and the Taylor series. Where did we begin that process? Well, we began it with just polynomial approximations, which were kind of the building blocks, the first initial part of the Maclaurin series and the Taylor series. So I want you to show me how to build these things. So first I want you to build one based off of this character. And I say it's Maclaurin. I even tell you Maclaurin means the center is 0. And so there you go. So you have to get the function and its derivatives all the way up to the 4th derivative. Okay. So there's that. And you have to evaluate them all at the center. For Maclaurin, the center is 0. And then you have to put it into our formula for the Maclaurin polynomial. And if you want to, you can use little boxes. Okay, so we're all set up. Let's go at it. 7 cosine pi x. This will be, all right, so derivative cosine's negative sign, but then you also have a chain rule based off the guts there, the pi x. So it's going to end up being negative 7 pi sine pi x. Then you're just going to keep getting extra factors of pi, so that the next guy is going to be negative 7 pi squared. The derivative of sine's cosine. And then when you take derivatives of cosine, you're going to get an extra negative in there. So that's going to change over the positive. And then finally, 7 pi to the 4th cosine of pi x. Okay, great. Evaluate them all at 0. So cosine of 0 is 1, so this will be 7. Sine of 0 is 0. And then you just fill in the blanks. All right, 7, 0, negative 7 pi squared, 0, 7 pi to the 4th. You could literally leave it like that if you want. But if you're looking to go above and beyond, you can go ahead and simplify it a little bit. Okay, and that's good enough. You don't have to multiply out the factorials. No. I'd rather see the factorials. All right, number 12 then, it gives us, we want a Taylor series now. Okay, so Taylor just means it has a non-zero center. Again, I'm asking for a 4th degree polynomial. That's what the n value is telling you. It says n is equal to 4, so I want 4th degree. So you need 4 derivatives, and I want the center to be 2. All right, so let's go at it. I'll go ahead and set it all up and then do everything. Don't forget, when you do your polynomial, you can't just put x's. You got to put x minus 2's. All right, so you get -2, x to -3. Looks like there's kind of some factorial action going on. So again, notice I'm not multiplying anything out. It's so I can see patterns and see cancellations. Just be 1 over 2 squared. There's just no point in multiplying stuff out, in my opinion. A lot of the mistakes I see is because people multiply it out. So if you do multiply out, I literally have to go through term by term and make sure you multiplied correctly on all your terms. I mean, that's the point. That's why I don't want you to bother. For my own sanity, don't do it. And I mean, honestly, it's in your own best interest not to do it. Why? It's because here you can see there's cancellation between the factorials. You probably wouldn't have seen that if you had it all multiplied out, like 4 factorial is 24 to the 5th. And you can see the formula on the terms if you want to construct the summation notation. You know, and the denominator is going to be 2 to the n plus 1 or something like that. You know? You can lead a horse to water, but you can't make him drink at the end of the day. But I don't know. Anyways, let's clean it up a bit. So again, you can see there's these nice kind of simplifiable terms throughout. And that term there is usually, what is it? It's basically just n plus 1 factorial all over n factorial. So how would that pan out? That would just be n plus 1 times n minus 1, blah, 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 3 times 2 times 1, all over n times n minus 1, blah, 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 3 times 2 times 1. So basically, you're just left with that first number, the number up top. So let me write it out. So you get 1 over 2 squared minus 2 times x minus 2 all over 2 cubed plus the 3 factorial all over, and you can really think of 2 as 2 factorial. 3 factorial over 2 factorial is just 3. So you see the nice pattern emerging. And on top of that, if you simplified like the 2 all over 2 cubed right here, you wouldn't see that nice pattern like in the numerator. So it'd be 1, 2, 3, 4, 5. Because if you cancel it out, then you just don't see it. Anyways, again, me trying to sell you. Seems like I can't get people to do it. Maybe the people just don't care. Some people just don't care. They don't care about anything. I don't know. I'm getting older. Okay, so there it is in all of its glory. Let's move on. So at this point, we worried significantly then about intervals of convergence. Just basically, where can we use what will eventually be the Maclaurin and Taylor series in order to do approximations? Because if the thing ain't convergent, it's useless. All right, you're not going to be able to replace, you know, the natural log of x with the power series if it doesn't converge at a particular value of x, right? So that's the point of this kind of section of problems. We have the sum of, there it is, sum of 3x to the n all over 2n factorial from n equals 1 to infinity. Okay, so the workhorse for these problems is the ratio test. So I do the limit of a sub n plus 1. And one big difference here is you need to keep those absolute values in play, right? Times, we'll take the reciprocal of a sub n. And start simplifying. So this portion here will just give me 3x, subtracting the exponents basically. And I'm going to factor that part out of the limit. And then everything else, right, give myself a little more room. Noting that 2 times n plus 1 factorial is really 2n plus 2 factorial. What do I have then? So 2n factorial is 2n times 2n minus 1 times 2n minus 2, blah, blah, blah. 2 times 1. All over 2n plus 2. And I kind of just keep going until I see the cancellation. There it is. Do one more. Okay. So it looks like this 2n factorial part is right there. That's going to go away. I'm going to factor the 3x out of the limit, but in doing so I have to keep the absolute value on the variable part. And then that'll equal the limit of the absolute value of 1 all over 2n plus 2. I don't really need the absolute value now, so I'll just drop it. But that limit there is 0, okay? And that will be true for any value of x, because anything times 0 is just 0. So what does that tell me? That means the interval of convergence is everywhere. All values of x will work. So I could use that series if it represents a function. I could use it for any value that I want to approximate. Okay. Okay. Next. So it's easy when it converges nowhere or it converges everywhere. So the case where it converges nowhere, usually it will converge at the center, because at the center it will just equal 0. But the hard problems are the ones where you're converging on an interval, right? And number 14 is that flavor. Of that flavor. Okay. So you approach it the same way as before. Please note you will not include the -1. The absolute value gets rid of it. So I'll just have the x minus 3 to the n plus 1 all over n plus 1 times 7 to the n plus 1 times the reciprocal of a sub n. So it'll be 7n to the 7 all over x minus 3 to the n. Then I start simplifying. So first this part right here, that's just x minus 3 to the first power. Right, so I get the limit of the absolute value of x minus 3 to the first. This portion, the 7 to the n stuff, 7 to the n over 7 to the n plus 1 is just 1 over 7. So I have this 1/7 floating about. And then the leftovers, n over n plus 1. I'm going to factor out the first factor, the x minus 3. I need the absolute values on that character. Absolute value of 7 is just 7, so I can write it as 7. And then I have the limit of n over n plus 1. Circling high degree terms, I see that that limit is just equal to 1. So I have absolute value x minus 3 over 7 times 1, which is absolute value of x minus 3 over 7. This thing will converge in the interval between, oops, I can get rid of the absolute value. But no, I can't do that yet. All right, so hold on. It'll converge when this thing is less than 1. That's just the ratio test factoid. And then we can expand that and kind of get the radius of convergence. Adding 7, we get 10, and that adding 3 to all three sides, we get 10, and then -4 on the other side. Right, so the radius of convergence there, what is it? 10, this is 7. right? The radius converges to 7. We want the interval convergence, though. In order to get the hands on the interval convergence, we need to investigate the endpoints for convergence. So I have to go over to -4, plug that into the original series. So I end up with the sum of -1 to the n plus 1 times -4 minus 3 is -7 to the n, all over n times 7 to the n. I'm going to simplify the heck out of that. So that -1 to the n plus 1 is, well, let's just leave that alone. And then the -7 to the n, I can kind of rewrite that as -1 times 7 to the n. And then I could rewrite that as -1 to the n times 7 to the n. Okay, so I have -1 to the n times 7 to the n, all over n, 7 to the n. Then the 7 to the n's will cancel. You can add the exponents of the -1. You get -1 to the 2n plus 1, all over n. And then what the heck is that numerator? So just kind of in my brain, -1 to the 2n plus 1 is equal to -1 to the 2n times -1 to the 1, which is -1 squared to the n times -1, which is -1 squared is 1. 1 to the n is just 1. And then that should just equal -1. Okay? So the series looks like it's just going to be -1 all over n. And of course, that guy is a multiple of the divergent harmonic, which is divergent. Okay, so that endpoint is divergent, and then you go over the 10. Plugging that into the original series, I get -1 to the n plus 1 times 10 minus 3 is 7 to the n, all over n times 7 to the n. Cancel out the 7 to the n's, and we get the sum -1 to the n plus 1, all over n. That is an alternating series, so tell your reader you got to do the alternating series test. Step 1, we look at the limit of 1 over n. Of course, that's 0. That's L over infinity. And then secondly, you look at a ratio of two consecutive terms, a sub n plus 1 and a sub n. Reciprocating, I get something that is definitely less than 1. So that tells me the terms are decreasing, and therefore, by the alternating series test, this particular series is convergent. Okay? So at the end of the day, the IOC, the interval convergence, is going to go from -4, not including -4, all the way up to 10, but including 10. Finally, at the end, we say, all right, how do we build these series representations for functions? Well, we just use the Maclaurin and Taylor polynomials and then extend them infinitely, right? So problem 15, the real only difference between problem 15 and the earlier polynomial problems is now you kind of have to put it in summation notation. If you don't put it in summation notation, I'll probably take off 1 point. I'm not going to beat you up over it, but you really should be able to do the summation notation if you're going to go on in math or. Okay, so that's my opinion, I guess, but it's a good opinion. Anyways, for this guy, we want it centered at 0, so it has to be a Maclaurin. And this time, you're not really constrained to how many derivatives you look at. You're going to just do as many as you need in order to identify a pattern. Okay, so here I am taking derivatives. The derivative of the exponential just gives you the exponential right back, but then you have to do a chain rule on the exponent. So the derivative -4x is -4. So at each derivative, you're getting an extra factor of -4. And I just keep going. Usually I do 4 or 5 derivatives. That turns out to be enough. And then you evaluate them all for Maclaurin at 0. and you need that nth term formula for the derivative to put in your summation. Okay, so if you want to, you know, I'm fine with you just kind of doing a fill in the blank. And then go plus this time, dot, 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 right? It goes on forever. But you should be doing this summation notation. And notice I tell you where I'm nice enough to tell you where to start your lower sum, the index on the lower sum. So I'm going to start at n equals 0, go to infinity. And this formula right here, this nth derivative is what's going to go in this blank. And then you have all over, well, it's the x to the n over n factorial, right? Those are those terms that you're seeing right here. That's x to the n over n factorial. The way they do it, usually written, is put the n factorial in the denominator and then x to the n over here. If you don't want to, just so there's a matter of consistency, because if you're always consistent, in my opinion, it's easier to memorize stuff. You could write it like this. I don't have any problem with that. I want to simplify it though, because if I simplify it, it's easier to work with. I can take it, put it in a computer, a lot easier. I can explain it to other people, and it's a lot easier. I don't know. Anyways, here we go. Right, so it looks like we have alternating negatives, so you're always going to have, in those cases, -1 either to the n or the n plus 1. So if the odd ones are negative, you're just going to put n, because any odd number you put into the exponent will give you a negative value out. Okay, and then we have 4 to some power, and it looks like when it's 2, you put in 2. When it's the third derivative, you put in 3. When it's the fourth derivative, you put in 4. So when it's the nth derivative, you put in n. Okay, okay, so we can copy and paste first if you need to. But ultimately, what we really want is a summation notation. And of course, I have to smoosh it in here. And there it is. There's really nothing to simplify here. Probably if I were going to rewrite it in the real world, I would want to put everything in the numerator like this. Okay. All over n factorial. But I guess that's my own personal, opinion. The boxes are fine, but again, like I said, if you don't show the summation notation, it's -1. Anyways, 16. So ln of x, this one will be Taylor because we want c equals 1. We want our lower index to be n equals 1. Okay, great. Here we go. Derivative ln of x is 1 over x, which is x to the -1. Again, go far enough so you can see a pattern evolve. Looks like there's some factorial action already happening. Evaluate these things at 1. And we're going to need that nth term formula on top of everything else. Unless you're just going to do the boxes and just give me the polynomial. So we could sort of start setting it up. The representation of f of x is equal to box plus box. It's Taylor now, so make sure you put x minus 1 plus box. Box plus dot dot dot, and of course our summation notation then. And I tell you to start the lower sum at 1, the lower index of the sum at 1. Okay, great. Let's go through. F of 1 is 0. So it'll be 1, -1, 2, negative 3 factorial, 4 factorial. So again, there's an alternating negative 1. I want the even numbers to be negative this time, so that's when you use n plus 1. And then, you know, for 3, you get 2 factorial. For 4, you get 3 factorial. For 5, you get 4 factorial. For n, you get n minus 1 factorial. Okay, so copy and paste this chunk in here. You can see there's a really nice cancellation going on with the factorials. So it seems like it's off, right? Oh, the first term is 0. Whoa, that was a huge mistake on my part. At least I caught it though, you know. The first term is 0. And then 1, negative 1, 2, but there's still that nice cancellation with the factorials. If you were to do the nice one, it would be negative 3 factorial. So you're always going to get just the leading number in the denominator. So the denominator will go starting here at 1, and then it'll be just 2, just 3, just 4, because the 3 factorial will cancel away. Okay. Anyways, of course, I didn't leave myself enough room in the stupid box. Let me augment it. So I need negative 1 to the n plus 1 times n minus 1 factorial. You can leave it like that, but you really should simplify it to be negative 1 to the n plus 1 times x minus 1 to the n all over n. And n equals 1 to infinity. Again, because n minus 1 factorial all over n factorial. Oops. That chunk will cancel with this chunk, and that's just 1 over n. Okay. Okay. So as usual, I will see you next time.